Hello, welcome guys, welcome back to Cheenta Statistics Analytics Department, and we are here with the 30th August. Today's problem ka solution, and this problem ka solution is actually about joint distribution ka CDF, and but it's something more than that. Okay, we will explore that. There's some extra added some extra part of it, which is I will show you. But if you have not done the problem, please come here and please don't do it now. Please stop it. Stop the video. What's the try out the problem and then watch the recording afterwards. Okay. So that's it. So let's get started with the problem, guys. And if you don't know what the problem is, you can just stop the video, okay, and see the problem. Okay. So let's do today's problem. And what's there in today's problem? So let's explore. So it's given that fx and GY are two one-dimensional CDF, and it can be shown. So actually show that this is the bivariate cumulative distribution function. Okay, so this is a problem. You have to show that. So how do you show that, guys? How do you show that it's a bivariate? How to show that it's a bivariate cumulative distribution function? So I have done a similar problem a few days back, that when you can see a function, a bivariate function is a bivariate CDF, and you have to check the very few conditions, that you have to check that f of x comma y, like h of x comma y, you have to check that h of x comma infinity is actually f of x, like the CDF of x, and h of infinity comma y is equal to g of y. And also you have to show that h of infinity comma infinity is 1, and h of minus infinity comma any y is equal to h of x comma any minus infinity is equal to 0. And what is h of x comma y? You know, like a joint CDF is defined as probability x less than or equal to small x and y less than or equal to small y. So you get this results, okay? You get this corresponding results as a by path of it. There's no right continuous condition in bivariate or that condition, because there is no right or left in two dimension. Okay, so when you're standing on the floor, there is no right and left. There's only right and left when you're standing on a line. Okay, so there is no right and left in standing on the floor on two-dimensional plane. So therefore there's a right continuous or left continuous or continuous condition in this. So you have to check this small four conditions to check whether it's a valid CDF or not. So let's check this conditions, and let's check whether how we can use this, and know that this f of x and g of y are actually the marginal CDF. Okay, so if you put x is equal to infinity, you will see that if you tell, that means it's what? So let's check it. Let me just copy and paste the part of the equation so that it's easier for us. So h of x comma y is defined as this. Let's understand the limits. So this is a continuous, it's not totally continuous, but you can do it like limit x tends to infinity. If you can try it out, you can see that it's limit x tends to, you just do limit x tends to infinity on h of x comma y. You will see it's limit x tends to infinity on this. G of y remains the same way, and by the limit assumptions 1 plus alpha, it's limit 1 minus limit x tends to infinity f of x into 1 minus gy. If you do this, you know that this is a valid CDF. Okay, fx and gy are CDF, fx and gy are CDF. So therefore limit x tends to infinity fx, since it's a CDF, we used one-dimensional CDF conditions, and you can get this is equal to 1, and therefore 1 minus this will go to 0. Okay, so therefore this goes to, and this is also equal to 1, so this goes to 1 times gy times 1, so which is equal to gy, and we can actually prove, therefore we prove that this is actually equal to gy. Okay, similarly you can do limit x tends to infinity. Let's give it the homework. Okay, it's very easy. It's a similar way limit, it's a symmetric in fx and gy in some sense. So like fx and gy in symmetric. So if you just do limit y into infinity, so limit y tends to infinity is a homework. Okay, it's a very easy way, exactly similar way. So you do limit y tends to infinity for the gy part. Okay, and you get 1 over here, you get fx, and you will have to get fx. So let's keep this an exercise for you so that you can easily do it, and it will be a good practice for you. Okay, and let's see that how let's see this condition, and it's very easy actually. You have to just take another x tends to infinity or y tends to infinity, and you get, since gy is actually CDF, so limit x tends to infinity and y tends to infinity will be actually equal to 1. Okay, so it's a really easy stuff to understand. And yep, so it's a continuous function in fx and gy, so therefore it will happen in that. So in fx and gy, not in x and y, but in fx and gy. So since x tends to infinity, fx goes to 1 and gy goes to 1 as y tends to infinity, so therefore this is a continuous function in fx comma gy. So therefore you can easily do it from there. Okay, you can easily understand it from there. It will turn out to be 1. That's super. That's super. That's a very good way of understanding that. And perfect. So we have done this 3 conditions. So let's see the let's check the other condition. Let's check limit x tends to y. Let's copy the function here again. So we want to do limit x tends to infinity, minus infinity, sorry, h of x comma y. And we do it the similar way, x tends to minus infinity, fx into gy into 1 plus alpha times 1 minus limit x tends to minus infinity, f of x into 1 minus gy. If you do this, you will see that this is going to 0, and the rest doesn't matter actually. So this is going to 0, so therefore this is going to 0. Similarly, you will see for limit x y tends to infinity, this will go to 0. And that's exactly what we need over here. That's exactly what we need over here. And therefore, we sort of, using this information, we sort of prove that this function is actually a valid CDF. But there is a very important question left. So we have not used till now the usefulness of alpha. Okay, so why the condition alpha less than equal to 1 is required, and that in like needs much more sophisticated understanding of the whole thing. So that's why we will understand. It's a real analysis mixed probability problem. So the real analysis part is an extra part for you. If you're interested in this problem, you can explore. So we get why alpha is less than equal to 1. This condition is there. Let's check that. What will happen if alpha is not there? Alpha condition is not there. So understand something, that 1 minus fx is less than equal to fx, 1, sorry, and 1 minus gy is less than equal to 1, similarly, right? So, and both are positive. So therefore, this one is less than equal to 1 plus alpha times 1 times 1. This under wala part, not the bahar wala part. So this is less than equal to what? 1 plus alpha. This is equal to 1 plus alpha. Now let's say is alpha less than 1, then this will become what? Less than 0. But h of x comma y, we have already proved it's a bivariate CDF. So it cannot be less than 0. That's the first condition. A CDF cannot be less than equal to less than 0, not equal to, less than 0, if alpha is less than 1, minus 1. So therefore alpha must be greater than equal to minus 1. So what about the upper bound? And the upper bound needs a much better understanding. So we have done this. We have to now to show, we will now show that alpha must be less than equal to 1. And why is that true? Why is that true? An intuitive understanding can be the following, that understand that if you make alpha very large, if alpha doesn't have an upper bound, you will see that this quantity will exceed beyond 1. If alpha is very large, this quantity will be exceeding beyond 1. Okay, like this total quantity. But h of x comma y is a CDF, so it must be between 0 and 1. Okay, so for the lower bound, we have seen the alpha must be greater than equal to minus 1. But for the upper bound, what is the good upper bound? And The given condition tells that its good upper bound is 1. But let's check that. Let's mathematically explain that. The question was that fx and gy can be actually any CDF. The fx and gy can be actually any CDF. Okay, so we will take a very special CDF. The CDF is, let's take the random variable x follows indicator or delta 1 or delta 0. What is delta 0? Delta 0 is a random variable which takes value 0 with probability 1 and yeah, it takes the value 0 with probability 1. Okay, rest with probability 0. So therefore, if you try to draw the CDF of this function, the CDF of this function looks like this. It's 0 if x is less than 0, and as x happens, the probability shoots up by 1, and it's 1 if x greater than equal to 0. This is the CDF. So if you consider the CDF, let's try to write down h of x comma y. H of x comma y was what? H of x comma y was this. So let's write down h of x comma y in this case. So we have to make two conditions, x less than 0 and x. So x less than it will be 0. For x greater than equal to 0, you can understand it's 1. So it will turn out to be g of y. It turn out to be x is yeah, it's 1. So it will turn out to be, I am doing something wrong. It's turn out to be z of y. Yes, it will turn out to be g of y. So you can understand from here, okay, there is a conditional alpha. I did some mistake in the calculation then while I was doing that. Just give me a minute. Okay. So, okay. So, yeah, I did some mistake. So, you can understand from here it's g of y, so it's less than equal to 1. So, I was trying to understand why this alpha is greater than equal to 1, less than equal to 1 condition is really needed. So, let me think about it. So, let's check this example that let's take this example. What if f of x times, or let me think, just give me a minute, 1 minus fx, and okay, so let's take uniform random variable. I don't know whether it will really work or not, but let's take uniform random variable. X follows uniform random variable and y also follows uniform random variable. So what happens is that small f of x is equal to x and g of y is equal to y. Okay, so what we get over here is the following, that h of x comma y is actually xy, okay, xy into 1 plus alpha 1 minus x into 1 minus y. So let's try to understand this function. When understand that fx, but x is less than equal to 1 and greater than equal to 0. Similarly, y is less than equal to 1 and greater than equal to 0. So we are trying to understand this function to be very specific. We're trying to understand this function to be very, very specific. So how to understand this function? How to understand this function? So if you observe over here, let me think. So my guess is that if alpha is less than equal to 1, this will turn out to be, if alpha is less than equal to 1, this will turn out to be, or greater than 1, this will turn out to be less than, like, more than 1 in some sense. So what we can do is that we can do some inequalities. And Okay. So xy must be less than equal to 1, and alpha, so we need to have an upper bound of alpha. So we need to have upper bound of alpha. Okay. So this is less than equal to 1. Xy is less than equal to 1, and x into 1 minus x. Okay. What I personally think is that if we take some special functions like this, I think it will be easier for us to really get that whole thing out here in terms of alpha. Um, if x is equal to 1. Yes. So, okay, so without waste your time, what I will do is I will come back with a solution, and I will make new video on it, okay? So in the meantime, stay tuned and stay blessed.